Hello, in this video I'm going to be solving exercise 6.2.11 from Jiří Lebl's notes on Diffy Qs. So here we're given this function f of t defined piecewise as follows, and there are three parts to this exercise. So part A, we need to sketch the graph of f of t. Part B, we need to write down f of t using the Heaviside function. And then part C, we need to solve this ODE here using the Laplace transform. So let's begin with part A. So in general, to sketch the graph of a piecewise function, all you're really doing is you're sketching the whole graphs of each of the pieces, but then when you're stitching together the graph of your actual function, you're only going to consider the pieces over their corresponding intervals. And let me show you what I mean by that. So I'm going to take a graph, or an xy plane rather, and let me add some coordinates, 2, 4, 3, and then right here, 1, 2, 3. Each of these tick marks will represent a distance of 1 for me. So what I'm going to do is I'm going to start with each of the different pieces of my graph, and I'm going to draw those separately with dotted lines. Why am I doing dotted lines? Well, I'm not going to want to include the whole graph in my final sketch of f of t, because I'm only interested in the portion lying above whatever interval this piece is given for. So in this case, this interval is from 1 to 2. So if I add tick marks here, this is the graph of y equals t minus 1 squared. But I only want the portion from 1 to 2, so I'm going to add, or I'm going to color in that portion as follows here, right here. I'm going to add an open circle here at 2 for now because we don't include this endpoints, but we'll see in just a bit that at least for this function, this hole does get filled in. Okay. Now let me move on to the next function. It's 3 minus t. This one has a graph that looks like this. And just like the other function, okay, so this is 3 minus t. For this one, I only care about the portion of the graph from 2 to 3. So once again, I'm going to take my red pen, and now notice that the value of 3 minus t is equal to 1 when I plug in t equals 2. So I do end up filling this red circle, as I mentioned. And I'm going from t to 3. So now we're going to go over here. And I'm going to draw an open hole right here for now because we don't include the endpoint 3. Finally, this function is 0 otherwise. So anywhere outside of these two intervals, my function should be 0. So to indicate that, well, we would just extend this function off to plus and minus infinity like this. And so the red curve altogether is the graph of y equals f of t. Okay, that's straightforward. What about part B? So now we need to write down f of t using the Heaviside function. And as a reminder, this Heaviside function here is given as follows. So it's denoted in our notes by u, and this function is 1 if t is bigger than or equal to 1. It's going to be 0 otherwise. So therefore, if you were to sketch this function on the xy plane, it would look something like this. Like maybe this is 1. The function would look like this. Goes to 0 until it reaches 0, and then it jumps up to be 1, and it continues off as 1. This is y equals u of t. But again, what we need here is to express f of t using this function. How are we going to do this? Well, the key here is to express each of the pieces first individually, using this Heaviside function. And so let us go ahead and do this. So the key express each piece t minus 1 squared, 3 minus t, using the Heaviside function. We're going to see what I mean by this in just a moment. But first, okay, first thing we need to note is the following. So note that if I have two numbers a and b, and a is less than b, then the function u of t minus a minus u of t minus b, it's not difficult to check that this function is 1 if t is between a and b, but not including b, and this function is 0 otherwise. The reason this is useful is because you might notice, and oh, here, let me erase this. This is for part C. So let me copy down this result right here over to the next page. Oh, you can't actually copy. Oh, wait, maybe you can. Here we go. Okay. So now I copied it. Let me paste it over here so we have it for future reference. Because this function is 1 on this interval and it's 0 otherwise, it follows that if I multiply by any function, let's call it x of t, or maybe g of t, just to not confuse with the solution to our ODE. If I multiply g of t by this function here, well, on this interval, this part is equal to 1. So then I'm doing 1 times g of t, which is just g of t. So we get g of t if t is between a and b, but not including b. And similarly, because this difference of Heaviside functions is 0 everywhere else, if we multiply that 0 by g of t, we're still going to get 0. So this is 0 otherwise. But what this means is that now I can construct examples of functions that are exactly what I need them to be on whatever interval. So for example, let's go back over here, and I note that I want my function to be t minus 1 squared on this interval here. What I'm going to do is I'm just going to take that piece, t minus 1 squared, and I'm going to multiply it by the corresponding function of this form that encodes my interval. So over here in the problem, it was the interval from 1 to 2. So I'm going to do u of t minus 1 minus u of t minus 2. And so from our calculation just now, this is going to be t minus 1 squared if 1 less than or equal to t less than 2, and it's going to be 0 otherwise. And we can play the same game with our other piece. If we take 3 minus t, now we want this piece to appear on the interval from 2 to 3. So I'm going to do u of t minus 2 minus u of t minus 3. And this is going to be 3 minus t if 2 is less than or equal to t less than 3. And it's going to be 0 otherwise. Okay, so we're almost finished. We're getting surprisingly close to what we want because these functions are doing what we want them to do on their respective intervals. But now we need to combine them somehow to be able to get f of t, to have it be this on this interval, be this on this interval, and 0 everywhere else. Here, what we're going to do is we're just going to add up these two pieces. And this gives me f of t, so I'm going to need some space. F of t is equal to t minus 1 squared u of t minus 1 minus u of t minus 2 plus the second piece, u of t minus 2 minus u of t minus 3. And this, by adding them in this way, we get exactly the expression for f of t that we need as from this piecewise function in terms of the Heaviside function now. And we can check this easily. So let me write this in blue. So here's a check. If t, or if t is between 1 and 2, then this part is 1 by our calculation up here, right? So this part is 1, sorry, not 0. But on the other hand, this part is going to be 0, because if t is in this interval, then t is less than 2. So t cannot be in this interval where t is bigger than or equal to 2. So this gives me u of t minus 2 minus u of t minus 3 equals 0. Therefore, this part becomes 1, this part goes to 0, so this term goes away. So f of t equals t minus 1 squared times 1 plus 3 minus t times 0. And this just gives me t minus 1 squared, which is exactly what we wanted, because from our piecewise expression, we want f of t to be t minus 1 squared on this interval here. Similarly, if we have t between 2 and 3, then now this part is 1. Now it's this part that is 1. But the other parts, this one right here, is going to be 0, because if t is in this interval, then t is bigger than or equal to 2. So t cannot be less than 2, and in particular, it cannot be in this interval. And therefore, when we calculate, this will be 0, this will be 1, so we get t times 0 plus 3 minus t times 1, which is 3 minus t. Nice. And then finally, we should check what happens when t is anything else. Well, now, both of these pieces are 0, because this is 0 outside of the first interval, and this is 0 outside of this second interval. So if you pick a value of t that is not in either of these intervals, then both of these difference of Heaviside functions must be 0. And let me write this out. Minus u of t minus 3 are 0. So now we get f of t is equal to t minus 1 squared times 0 plus 3 minus t times 0. And evidently this is just 0, which is exactly what we want, because again, we want our function to be 0 anywhere outside of these two intervals. Very nice. All right, let's now do part C. And as a reminder, for this part, we need to solve x double prime plus x equals our function f of t, where f of t is the piecewise function we were given, and we are subject to the initial conditions x of 0 equals 0 and x prime of 0 equals 0. Just going to double check that. Yes, good. And we're going to solve this with the Laplace transform. Okay. So taking the Laplace transform of both sides, we get L of x double prime plus L of x is equal to L of f of t. And this in turn, just using the usual formulas for the Laplace transform, this will be this plus capital X. And all of this is equal to the Laplace transform, and I'm going to plug in my expression for f of t in terms of the Heaviside function. T minus 1 squared, u of t minus 1 minus u of t minus 2. And then we had plus, so right here, where is it? We had plus 3 minus t, but I'm going to rewrite this as minus t minus 3, like this. You'll see why later on. And then this is u of t minus 2 minus u of t minus 3. Okay. And, okay, both x of 0 and x prime of 0 at 0. So these terms are going to vanish. And so the left side becomes, after we factor out the capital X, it'll be this. And the right side will be the Laplace transform of, and now I'm going to distribute t minus 1 squared into these Heaviside functions, and likewise for the negative t minus 3. That's going to give me u of t minus 1, t minus 1 squared, minus u of t minus 2, t minus 1 squared. And then we have minus, minus u of t minus 2, t minus 3, plus u of t minus 3, t minus 3. Which, by linearity, this is the same as L of u of t minus 1, t minus 1 squared, minus L of u of t minus 2, t minus 2, t minus 1 squared. And then over here, minus L of u t minus 2, t minus 3. And then plus L of u t minus 3. And then we have times t minus 3. Sorry for the small print. And finally, what does this give us? Well, we end up getting, well, actually, to solve for x of s, we first need to figure out what these Laplace transforms are. Now, here we need to remember something about the Laplace transform called the second shifting property. So this states that if a is a positive constant, then the Laplace transform of a function of this form, f of t minus a, is equal to, what we're going to do is take an exponential e to the minus at, where a is the constant that we're shifting by, and it's going to be multiplied just by the Laplace transform of f of t. The reason this is useful is because you might notice that this expression here is exactly in the form that is required for the second shifting property to apply. For this first transform, our a is 1, And so we get that L of u t minus 1 t minus 1 squared, just from the second shifting property, it's going to be e to the minus t. So there's no 1, I just dropped it because it's just a 1. And then we have the Laplace transform of t squared, sorry. Because we're plugging in t minus 1 into our f, which in this case is t squared. And this in turn is going to be, well, oh, sorry, not e to the minus t. These are supposed to be s's. Oops. S, and then s. And this in turn is going to be e to the minus s times 1 over s squared. Oh, sorry, 2 over s cubed. Okay. Similarly, over here, now we're going to compute the Laplace transform of the next term. So u of t minus 2, t minus 1 squared. Here, you might notice that we have a problem because the a that we're shifting by isn't the same in both of our functions. We can easily fix this, though, by instead making this so that it looks like t minus 2 plus some constant to cancel out whatever, or to bring things back to equality, rather. So I want this to be t minus 2, but we had minus 1 originally, so I need to add 1 to make that negative 2 become negative 1. And so now, by the second shifting property, notice here that my f of t is now going to be t plus 1 squared. So the Laplace transform of this is evidently going to be e to the minus 2s times the Laplace transform of t plus 1 squared, which in turn, if you FOIL this out and then you take the Laplace transform of each of the terms, you get 2 over s cubed plus 2 over s squared plus 1 over s. Using the shifting property for the other two terms, we get similar expressions. So let me just run through these really quick. U of t minus 2, t minus 3. This is going to be e to the minus 2s. And we're going to get, well, now it's the Laplace transform. So we need to rewrite this as t minus 2 plus 1, or minus 1, sorry. Now we're doing minus 1. And so then this will be the Laplace transform of t minus 1, which is e to the negative 2s, times 1 over s squared, yes, minus 1 over s. And then finally, we have the last Laplace transform, and this one's a lot easier because the things we're shifting by are already the same. It's just 3 in both cases, so it's going to be e to the negative 3s. And then we're doing the transform of t, which gives me e to the negative 3s times the Laplace, or rather 1 over s squared. Putting these together, we get that the Laplace transform of f of t, our function, is just going to be e to the negative s times 2 over s cubed minus e to the negative 2s times all of that, 2 over s cubed plus 2 over s squared plus 1 over s, minus e to the negative 2s, and then here we have 1 over s squared minus 1 over s. Then finally, plus e to the negative 3s times 1 over s squared. And so now let's clean this up. I'm going to clean this up to collect all of the exponentials into the same term. So I'm going to group together all the e to the minus s's in one term, all of the e to the minus 2s's in another term, and all the e to the minus 3s's in the last term. So this will be e to the minus s times 2 over s cubed. And then we're going to have minus e to the negative 2s, 2 over s cubed plus 2 over s squared plus 1 over s, plus 1 over s squared minus 1 over s. And then finally, plus e to the minus 3s times 1 over s squared. We'll see why I'm grouping these terms together by exponentials like this in just a moment. But for now, okay, these terms cancel. And then 2 over s cubed and 1 over s squared become 3 over s cubed. And so this simplifies to e to the minus s times 2 over s cubed minus e to the minus 2s, 2 over s cubed plus 3 over s squared, plus e to the negative 3s times 1 over s squared. And once again, the left side for us was originally this. Therefore, solving for x of s, what do we get? Well, we get e to the minus s times s cubed. And let me go ahead and actually, let's factor out the constants. 2e to the minus s, and then we're going to have s cubed s squared plus 1 over 1. Minus e to the negative 2s, and then I'm dividing both of these terms by s cubed. Or actually, because we have, here, I'll write it this way. So I'm going to do maybe it's better to leave it this way. I apologize. I was trying to decide what might look nicer. Here we go. So now, dividing both of these terms by this, we're going to get this, okay? And then finally, plus e to the negative 3s, and then we have s squared plus 1, all over 1. And so this is the Laplace transform of our function. Okay. So now, let's not immediately start expanding this just yet. I want to illustrate something, okay? So let's take inverse Laplace transforms. You'll see why we're doing this in just a moment, but carrying on, if we take inverse transforms, well, we get inverse transform e to the minus s times 2 over s cubed s squared plus 1 minus e to the negative, inverse transform e to the negative 2s. Then we have 2 over s cubed s squared plus 1 plus 3 over s squared plus 1 plus e to the negative 3s, 3s, 1 over s squared plus 1. Okay. Let's pretend for a moment that we found the inverse Laplace transform of 2 over s cubed s squared plus 1 or actually even better. So let me denote this by f of s. And even better, actually what we can do is, I'll leave it like this. Let's name this f of s. Okay. This also is f of s. Let's call this over here g of s, so that this is 3g of s. And let's just pretend for a moment, or even better, not even pretend. Something you might notice is that these are Laplace transforms for some functions. We don't know what functions have these Laplace transforms yet, but if we could find them, so I guess even that we found L inverse f of s and L inverse of g of s, and let's call them, and I guess actually f might be a bad name because I want to use little f for the inverse Laplace transform. So let me call this h instead. Call the inverse Laplace transforms h of t and g of t, respectively. Then, okay, returning to the shifting property, we have this, right? But notice that if I take inverse transforms here, this also says that ut minus a f of t minus a is the inverse transform of e to the minus as capital F of s, where capital F is just the Laplace transform of little f. Therefore, it follows that the inverse Laplace transform of e to the minus s h of s, which you might notice is exactly this inverse Laplace transform here, by the shifting property, now just applying it in reverse, this will be u of, well, here the exponent in front of the s is 1, so it'll be u of t minus 1, h of t minus 1, and then L inverse of e, if we look at the last term now, e to the minus 3s times g of s equals, well, now this is 3, so this will be u of t minus 3, g of t minus 3. And then this final inverse Laplace transform is that of h of s plus 3g of s. So this will be e to the 2s, and then we have h of s plus 3g of s. Well, this instead, so here we have to break this up first. So this will be the inverse Laplace transform of e to the minus 2s, h of s, plus 3e to the negative 2s times g of s. And by linearity, this is going to be equal to u of t minus 2, h of t minus 2, and then we're going to do plus 3u of t minus 2, g of t minus 2. And so then, let me add another page. Then it would follow that x of t is exactly, well, we just now have to do this minus this plus this from this expression up here. So we're going to get, once again, u of t minus 1, h of t minus 1, minus, and then we have u of t minus 2, h of t minus 2, plus 3 u of t minus 2, h g of t minus 2. And then finally, plus, right here, plus this term. u of t minus 3, g of t minus 3. And then we're done, because now we have found x of t. Okay, but all of this is futile if we don't know what little h is. So, and little g. And as a reminder, h of t is the inverse Laplace transform of h of s, which in turn was the inverse Laplace transform of 2 over s cubed, s squared plus 1. And similarly, g of t is the inverse Laplace transform of g of s, which for us was the inverse Laplace transform of 1 over s squared plus 1. So both of these calculations are just going to amount to doing partial fractions on each of these, and then taking the inverse Laplace transform. I'm only going to work through the calculation for this inverse Laplace transform, as the second one is similar. I encourage you all to pause the video right now and actually calculate the inverse Laplace transform of g of t and of h of t, and only return to the video when you've given those a shot. Okay, but now proceeding on, let me calculate the inverse Laplace transform of this function here. And okay, if I do partial fractions, I have this repeated s factor, so I have to account for that. B over s squared plus c over s cubed plus, and then I have this irreducible quadratic, so I'm going to add ds plus e over s squared plus 1. So I'm adding a linear term instead of a constant. If I clear denominators by multiplying both sides by s cubed, s squared plus 1, I get 2 equals a s squared plus 1 plus b s squared plus 1 plus c s squared plus 1 plus ds plus e times s cubed. And so at this stage, we could expand the right side if we wanted to and solve for the constants that way. I think that would be extremely painful because we would get 5 equations and 5 unknowns, and that would be, that could be rather very tedious to solve for. So instead, what I'm going to do to at least simplify this task is I'm going to teach you all a trick. My students might remember this from discussion. The viewers might also remember this from Calculus 2 or a similar class. The trick is to plug in values of s that make the right side vanish, or terms on the right side vanish. What do I mean by that? Notice, for example, that if I plug in s equals 0, then because of this s squared here, this whole term will be 0, this term will be 0, this term will be 0, and only this term will not. So if I plug in s equals 0, I get 2 equals, well, this will be 0, 0, 0, and then 0 squared plus 1 is 1, so I'm just left with c. And that immediately gives me the constant for c. So now I know that c is equal to 2. Very nice. Let me jot this down up here. And I'll even write it in green so that we know we just found it. There we go. So if I plug in s equals 0, I get 2 is equal to c. Okay. But it seems like that's the only convenient value that we can plug in. I mean, what else can we do? Well, if you're comfortable with complex numbers, another thing we can do to try and get some more values is to plug in complex values. So here, if I plug in s equals I, well, s squared plus 1 is going to be 0 because I squared plus 1 is equal to 0. And likewise, this will be 0, this will be 0, and all I'm left with is the last term, which is 2 equals di plus e times I cubed. And this is di to the fourth plus ei cubed. And then just from properties of complex numbers, well, I to the fourth is equal to 1. And then I cubed is negative I, so this is d minus ei. Okay? But the only way for this complex number to equal this left side is if the corresponding real and imaginary parts are equal. Now, the real part of 2 is 2, so I need d is equal to 2. And let me actually write this too, so equating real and imaginary parts, I get that 2 equals d, and also that e is equal to, well, it's going to be 0 because there's no 0 on this side. So e will equal 0. So then going up here, what do I get? Well, I'm going to get 2 for d, and I'm going to get 0 for e, so there's no more e. And all that remains now is to find a and b. But we've exhausted all of the values that we could plug in to make these things 0. Some of you might wonder if we can plug in negative I, which is another root of this. And we could, but let me show you what happens if we do that instead. So s equals negative I. We get 2 equals, well, again, all of these terms go to 0. And all we're left with is this last term here, which for negative I gives us negative di plus e, and then we have negative I cubed. And this will be d times negative I to the fourth plus e negative I cubed. And negative I to the fourth is still going to be 1, so this will be d. And then e times negative I cubed is going to be e times negative 1 cubed times I cubed. And we know that I cubed is negative 1, and negative 1 cubed is, I cubed is negative I, and then negative 1 cubed is negative 1. So this will be d plus ei. And once again, if we equate real and imaginary parts, we just end up with what we already found here, that d equals 2 and e has to be 0. So we don't gain any new information. So at this stage, the best we can do now is to actually go back up here to this equation, which I'm going to duplicate, and just proceed to plug in the coefficients we know already, and then solve for the other two using our usual methods. Okay. So what do we know? We know that, and oh, I forgot to write d equals 2. Oh wait, I already wrote it down here. Oops. So we know that c equals 2, so I'm going to plug this in. I know that d equals 2, and I know that e equals 0. And so if I start expanding this, I'm going to get a s squared, or s to the fourth, sorry, plus s squared, plus b, and then s cubed plus s, plus 2s squared plus 2, plus, and then we have 2s just here times s cubed, that's 2s to the fourth, this is 2s to the fourth. And all of this should be equal to, well, if we distribute the constants, as squared plus bs cubed plus bs plus 2s squared plus 2 plus 2s to the fourth. And then combining like terms, we get a plus 2s to the fourth plus bs cubed, and then our squared terms are a and 2, so a plus 2s squared. And then for the linear terms, we just have bs plus 2. And so if we equate the coefficients here with those on the left side, we see that a plus 2 must be 0 and b must be 0. Which gives me that a equals -2, and again, b is equal to 0. Okay, so now that we've actually calculated this partial fraction decomposition, now we've done the heavy computational work, and we can proceed to actually find the inverse Laplace transform for this function. So this will be, by our calculation, well, we have that a is equal to -2, so we're going to have -2 over s. And then b is 0. We just found b to be 0, so there is no term right here. And then we have plus 2 over s cubed. And then finally, d was 2 and e was 0, so we get 2s over s squared plus 1. Therefore, if we take the inverse Laplace transform, this is going to give me, well, just consulting what we know about inverse Laplace, this one is going to be just -2. And then we're going to get plus t squared, and then plus 2 times the cosine of t, right? Once again, I will leave or I hope everyone got a chance to try and compute the partial fraction decomposition for this other Laplace transform that we need, which was, if you'll remember, we had 1 over s squared plus 1. And if you do the same calculation, or like partial fractions and whatnots, this one works out to be t minus sine of t. And therefore, well, remembering that what our solution was, it was all of this. It was all of this. Well, now we just need to plug in, okay. So this, all of this is our h of t, and this was our g of t, right here. So then, just remembering what our x of t was, we figured out that it was exactly all of this. So we had u of t minus 1, h of t minus 1, minus u of t minus 2, h of t minus 2. So here I'm distributing this minus over into the inside. Minus 3 ut minus 2 g of t minus 2. And then finally, plus u of t minus 3 g of t minus 3. And we just need to plug in t minus 1 wherever it occurs for our h or our t and so on. And this, finally, it's going to be a bit lengthy, is going to give me -2 plus t minus 1 squared plus 2 cosine of t minus 1 minus u of t minus 2 times -2 plus t minus 2 squared plus 2 cosine of t minus 2. And then I'm going to do the other two terms on the next line. So this will be minus 3 ut minus 2. And then we have t minus 2. So now we're plugging into g of t here. T minus 2 minus sine of t minus 2. And finally, plus u of t minus 3 times t minus 3 minus sine of t minus 3. And this would be our final answer. Okay, that wraps up this video. If there are any comments, please feel free to leave a comment. Or if there are any questions, sorry, please feel free to leave a comment. Otherwise, I will see you all in the next video.